guys moving the slides because sometimes they don't move. Perfect, perfect. Great. So welcome everybody to the afternoon session, the second day of our summer school. I'm very pleased to introduce Joao Luis Rosa, who is going to talk about relativistic fluid spheres with thin shells as black hole mimikers. So you can go ahead, Joao.
Thank you very much. So my name is Joao Luis Rosa. I am from Portugal, but at the moment I am doing my first postdoc in the University of Tartu in Estonia. And before I start, let me say that I am aware that some of you do not have a mathematical background and some others do. Nevertheless, I decided to keep the equations, well, just some of the equations in this presentation. So if you have a mathematical background and you are looking for more details, you will be able to see more details because the most important equations are here. But if you don't have a mathematical background, don't worry, I will explain everything qualitatively by words. So if you see an equation and you don't understand it, that's perfectly fine. You can just ignore it and I'll do my best to transmit the same information by words. And I'm sure, I hope most of you will be able to follow as well. So my work is about relativistic fluid spheres with thin shells as black hole mimickers. And let me start by giving you some motivation on why this topic is important and to review briefly the concepts we need to what's coming up next. So today we have plenty of observations from, for example, the center of our galaxy and from the center of other galaxies also. And also with the mergers of black holes in gravitational waves, we have a lot of observations that indicate that black holes do exist. And recently, for example, we have the observations from the center of our own galaxy. The star S2 is orbiting a very massive object in the center of our galaxy. And also, even more recently, we had the first image of a black hole shadow by the Event Horizon Telescope. And if you compare these observations with the predictions you have from general relativity, it is amazing how these observations are predicted by the theory. So one is usually led to affirm that black holes do exist because our predictions match the observations pretty well. But black holes, although they can be represented in this way and we have observations that are so consistent with the predictions, black holes do have problems. They are not just sunshine and rainbows. And two of the most important problems of black holes are the existence of these two things that are event horizons and singularities. So an event horizon is basically a surface around the black hole that works as a one-directional membrane. You can go inside an horizon, but you cannot go out. And the space-time singularity is a point in the center of this black hole. For static black holes, it's a point in the center where the density is infinite. So it kind of feels like this object has collapsed infinitely to this point. And so these two features of black hole spacetimes are something that are not very well understood at the fundamental level. So they work mathematically, but when you try to make sense of what they mean or what these things mean physically, sometimes we get very confused because we don't know exactly what this means, and we actually call it singularity. The fact that we call them singularities, for example, it's kind of an indication that we really don't know what's happening there. And so there is one question that arises: would it be possible for us to create a model for a compact object that behaves exactly in the same way as a black hole does, but that avoids these problems in general relativity, for example? Because there are many ways of testing this problem. One can develop new models in general relativity. One can test different theories of gravity, and the objective is always the same: is to try to solve the problems that arise in general relativity, and in particular in black hole objects. So if we could find a model for a compact object in general relativity that behaves exactly as a black hole when seen from an exterior observer, but on the other hand doesn't have event horizons or singularities, this would be a very nice result, because we can explain the observations we have today without recurring to these properties that are not very well understood at the fundamental level. There were many different tests, many different models developed to try to explain this situation. One of such is the Schwarzschild fluid star. The Schwarzschild fluid star is a very, very simplistic model where you have a sphere of relativistic fluid with a constant density. And now the equations are going to start to appear, but don't worry, I'll try to explain everything by words as well. So anybody, even if you don't have a mathematical background, will be able to follow. So this star is divided into two regions, the interior region, where the fluid is. So if you imagine this star, this shell, this sphere of fluid in green will be the interior of the star. And then you have the exterior, which is basically vacuum. You can imagine this star as being roaming in a vacuum universe. And so there are these two regions. The outside region, for those of you who have a mathematical background, can be described by the Schwarzschild metric. The Schwarzschild metric is simply a spherically symmetric vacuum spacetime and static. And in the interior region, you will have a fluid with a constant density. So the metric that describes the spacetime is a little different. And for those of you who know these kind of metrics, these two spacetimes are represented by these two metrics. So you have a sphere of fluid with a constant density roaming around in an empty universe. And now you can ask, okay, of course, the density of this object is a constant, but what is the pressure inside this object? And the pressure is something that varies from the center of the object to the surface of the object. You can think of it as the sun, for example, because at the sun, you kind of define the surface of the sun as the region where the pressure goes to zero. And as you go inside the sun further and further, your pressure increases. So one can ask, what is the profile of the pressure as a function of the radius? And well, as you increase, as you go towards the center of the sun or the center of the object, the pressure will increase. And now you want this star to somehow replace your black holes in your observations. So you need this star to be as compact, as small as possible in order to be able to be undistinguishable from a black hole when this star is, for example, in the center of a galaxy, for example. The problem is that, and this is called the Bookdahl theorem, you cannot have a star like this with a size arbitrarily close to the size of a black hole. Because if you do so, if you compute the pressure at the center of this star, which, as I said, increases as you make the star more and more compact, you will see that the pressure of this star diverges when the radius of this star is smaller than the mass of the star times 9/4. So this is called the Bookdahl limit. If you have a star made of a constant density, and it extends to more than just constant density. If you have a star whose density is non-increasing, which is more or less what you expect, this star will develop a singularity if you try to force the star to be smaller than a certain radius. And this is called the Bookdahl theorem. So in conclusion, this star cannot be used to replace black holes in observations because you cannot make this star compact enough to replace black holes without developing also a divergence, a singularity in the center. So this star doesn't work. Now, the thing is, the Bookdahl theorem is based on a few assumptions. And one of the assumptions is that the density of this star must be non-increasing. So if we drop this assumption by somehow creating a shell of fluid inside or outside the star, we can avoid this assumption of the Bookdahl theorem, and we can create models for stars that are able to replace black holes in the universe. This is my objective. I will try to take the Schwarzschild star, drop one of the assumptions of the Bookdahl theorem, and create models that can be used to replace black holes that do not have any horizons or singularities. That's the objective of this talk. Now, very quick, I'm going to speak about the junction conditions. So as I said before, this star is divided into two regions. If you have this object roaming freely in the universe, you will have an interior region where the fluid is, and you have an exterior region, which is vacuum. And these two regions must be, let's say, glued together at the surface of the star. And this match between the two spacetimes must be a solution of the Einstein's field equations, because otherwise it's not a model in general relativity. So for you to be able to make this matching between the two spacetimes, you need to use the so-called junction conditions. So to understand better what these junction conditions are, let's imagine a spacetime, any spacetime, that is divided into two regions. Let's call the interior region V minus. This is the region where the fluid is, for example, in the case of the Schwarzschild star, the interior spacetime. And we have the exterior spacetime V plus. And V plus is, in this case, vacuum, so the universe outside the star. We define this surface in red, called sigma, as I call it here, sigma. This is the surface that separates the interior and the exterior spacetime. So in this case, it would be the surface of the star. And now we have a vector NA, which is the vector perpendicular to the surface of the star. In the interior region, we have coordinates x minus. In the exterior region, we have coordinates x plus. And in the surface, in red, we have coordinates y. Now, what do we have to do in order to guarantee that the spacetimes v minus and v plus can be glued together at this hypersurface? Well, there are two main quantities we have to analyze. One of them is the induced metric, and the other is the extrinsic curvature. For those of you who don't have a mathematical background, let me translate what this means by words. So the metric is a quantity that tells you how distances behave, so how to compute distances in a given spacetime. The induced metric is a particular form of this function that tells you how to compute distances in a surface with one less dimension than the full spacetime. So if your spacetime here is 4 dimensions, so 3 spatial dimensions and 1 time dimension, this induced metric represents the distances in this sphere here, in this surface of this sphere. So this is going to be 2 spatial dimensions and 1 time dimension. So what you want is this induced metric to be a continuous function, which more or less makes sense, right? If you are moving from the interior to the exterior of a star, you expect your distance, the distances you move across, to be continuous. You don't jump from one point to the other like teleportation or something. You have to this function must be a continuous function, and so this is what you expect from these two spacetimes to satisfy. The metric, the distances at the separation between the two spacetimes must be continuous. Now, the second quantity, called the extrinsic curvature, is a little more complicated to view intuitively, but it means basically that this surface that separates the two spacetimes has a continuous curvature. And this is exactly what happens in the Schwarzschild star. But this quantity, this extrinsic curvature, it is forced to be continuous in the case of the Schwarzschild star, but that is not mandatory. That just simplifies the things. So what I'm going to do to find more general models for stars, more general than the Schwarzschild star, is to drop this assumption. Let's forget about extrinsic curvature. Let's just confirm, let's just guarantee that the induced metric, or in other words, the distances, are continuous. They are a continuous function. Let's drop the second assumption and let's see what kind of models we can find for stars using this assumption. And what we verify is that we can do so perfectly. They are still solutions of the Einstein's field equations. The difference is that there will be what we call a thin shell in the separation between the two spacetimes. So instead of having interior spacetime glued to an exterior spacetime with nothing in between, you will have a thin shell, like a shell of fluid separating the two spacetimes. And this thin shell will have certain properties that we have to study, and we have to guarantee that they are physically relevant. For those of you who have a mathematical background, the stress energy tensor of the thin shell is given in terms of the extrinsic curvature. So just for you to have this in mind. Now, in this talk, I'm going to introduce two types of models that can be obtained using this formalism. The first one is a model where we compress the exterior layers of the star. So let's take a star like this one. This star has a radius bigger than the Bookdahl radius. So if you don't remember, the Bookdahl radius means that if the star has a radius smaller than the Bookdahl radius, it will develop a singularity inside. So in this model number one, we start from a star with a radius bigger than the radius of Bookdahl, and this guarantees that there are no singularities inside the star. And then what we do is to collapse the exterior layers of the star into a thin shell. In the end, we obtain a star that has a radius smaller than the Bookdahl radius, but it still does not have a singularity because we guaranteed to start from a star that does not have a singularity inside. So this is going to be our model number one. Instead of having just a shell in vacuum, just a sphere in vacuum, we have a sphere surrounded by a shell in vacuum. That's model number one. For model number 2, we are going to do something slightly different. We start from a star with a radius smaller than the Bookdahl radius. So in this star, according to what I said before, this star will have a singularity somewhere inside, right? Because the radius is smaller than the Bookdahl radius. And then what we are going to do is to open a hole, create a vacuum bubble inside this star to remove the singularity from inside the star. And in the end, we got some kind of a hollow sphere supported by, again, a thin shell of matter inside the star. So in the end, what we have again, we end up with another fluid star, another fluid sphere with a radius smaller than the Bookdahl radius, but again, it doesn't have a singularity and it doesn't have an event horizon. So these two models could, if they work, and we are going to see if they work or not, if they work, they could be able to replace the models for black holes without having singularities and without having event horizons. So the first thing we have to do to guarantee that these models are physically relevant is to verify if normal matter, the matter that we see today, matter with positive mass, matter with positive energy density, matter like we see in the universe, would be able to create this kind of spheres. This is the first thing we have to do. And the second thing we have to do is that even if these objects can be formed by normal matter, we have to guarantee that these objects are stable, because if they are unstable, it really doesn't matter, they just disappear. So these are the two things we have to guarantee. Let's jump into thing number 1. Let's verify that these objects can be made of matter as we observe it in the universe. So matter with positive average energy density, or in other words, matter that satisfies the null, weak, and strong energy conditions. So for model number 1, sorry, I have a little cold, so if you hear me sneezing too much, I'm sorry. For model number 1, these are the results we have. So in the plot here on the top left, I have the density of the shell. So this extra shell that appears in the separation between the two spacetimes. Here we have the density of this shell as a function of the radius of the shell for 4 different values of the initial radius of the star. And in here, it's exactly the same thing, but instead of the density, we have the pressure of this shell. So we see that the densities are positive, the pressures are positive, and now one can ask, is this combination of energy density and pressure or tension consistent with the energy conditions? So is it possible for matter as we observe in the universe to satisfy this kind of energy and tension relationship? And the answer is yes. In this plot here on the bottom left corner, we have the sum between the density and the pressure as a function of the initial radius of the star and the radius of the shell. And as you can see, this combination is always positive. So this means that the weak energy condition is always satisfied. And so for any observer moving around this star, he will always observe a positive average energy density. So this is the matter that we are used to in the universe. For the strong energy condition, the expression is very similar, but instead of being just the density plus the pressure, we have density plus twice the pressure. And in this case, again, we are expecting the result to be a positive value. But again, if we compute this, we can see that no matter what combination of the initial star radius and the shell radius we consider, the result will always be a positive value. So again, this energy condition is satisfied. And so this first model can be constructed with matter as we observe in the universe, so non-exotic matter. If we now look into the second model, which is a little more esoteric, remember this is the one where you remove the singularity from inside the star. It's something more difficult to imagine how it could appear in nature, but nevertheless, let's verify if it works or not. The results are a little different, and this is what we get. So in the left, again, we have the density of the star, and in the right, we have the pressure, not the star, the shell, the density of the shell. And on the right, we have the pressure on the shell. And we can see that the behavior changes a little bit. So the density is still positive, which is good. The pressure is also still positive, which is also good. But as you can see, there are some values here where the pressure diverges. This corresponds exactly to the fact that there is a singularity inside the star. Remember, we start from a star that is so compact that it has a singularity, and then we want to remove the singularity. So this is what we expect. We expect that this star somewhere has divergences. This corresponds to the singularity. And now we have to remove this singularity, okay? Now let's see again if these two results, the result for the density and the result for the pressure, if they are consistent with matter as we observe it in the universe. So again, we plot the weak and the strong energy conditions, and now the results are a little different. There is in fact a region in here where the energy conditions are violated. So in below this white line here, the weak energy condition is violated, and this line is exactly the same for the strong energy condition. Below this line, the strong energy condition is also violated. So one can ask, okay, does this mean that there are combinations of parameters for which we have matter different from what we observe in the universe making these objects? And the answer is, well, not really, for one simple reason. This line here corresponds exactly to the radius where the singularity is. And remember, we want to remove the singularity. So if we want to remove the singularity, we must always be above this line. And so, as you can see in these two plots, if you are above this line, you are removing the singularity, and the result is positive. So if you do remove the singularity from the inside of the star, automatically the star is made of matter as you observe in the universe, right? If you are below this line, this means that you are not removing the singularity. And as a consequence, the star will be made of matter that you don't observe, exotic matter. So as long as you guarantee that the singularity is removed from the star, you will get a star that is made only of regular matter, non-exotic matter. So again, everything seems to hold. So far, we have proven that these two models, they do satisfy the weak and the strong energy condition, and so they are made of non-exotic matter. This is the first result that we get. This is the first important result that we have in these models. Now, as I said before, this is not enough. It's not enough that the models are made of good matter, of regular matter, matter that we observe. We also must prove that, that the models are stable. Because even if they are made of good matter, regular matter, if these objects are unstable, they are unable to replace black holes in the universe. Because when we observe black holes, these black holes, the big ones, for example, they are in the center of galaxies. So they have been there for millions and millions and millions of years. So they must be stable. If they were unstable, they would already be decayed or something else. So our results, our models to be able to replace black holes in the center of galaxies, for example, we need to guarantee that our models are stable. Because even if they are made of good matter, if they are unstable, they are not able to replace the black holes that we know or we observe are stable. So next thing we have to do, we have to perform a stability analysis of these two models and verify if the models are stable. So what does it mean to make a stability analysis? Well, it might sound complicated, but it's actually pretty simple. Imagine, for example, a pendulum. If you have a pendulum and and the pendulum is not moving, it is at its equilibrium position, right? So for you to verify if this pendulum is stable or not, what do? Well, you take the pendulum, you move it a little bit to the left or to the right, and let it go. What happens? Well, the pendulum starts moving around the equilibrium point. So the pendulum is somehow stable, because when you move the pendulum away from its equilibrium position, the pendulum will go back to the equilibrium position. It might take a while, might take a few oscillations, but as friction enters the game, the oscillations will be smaller and smaller, and in the end, the pendulum will return to its initial position. So the pendulum is stable. On the other hand, for example, imagine that you are trying to balance a pen in your hand, like a pen like this. So if the pen is perfectly balanced in your hand, the pen will be static. But if you move the pen just slightly to the left or slightly to the right and you let it go, the pen is going to fall for one side or the other. So the pen never returns automatically to its equilibrium position. So the pen balancing a pen in your hand is an unstable point. It's an unstable equilibrium. So if you move away from the equilibrium, it never returns to the equilibrium. So this is exactly what we are trying to do with these stars. We take the star, we move the star a little bit outwards or a little bit inwards, and we verify what happens. If we increase or decrease the radius of the star just a little bit, and the star oscillates but comes back to the initial radius, then the star will be stable. If you move the star a little bit to the inside or a little bit to the outside, and the star either collapses or expands forever, then the star is unstable. Simple as that. So mathematically, what you have to do is to find the equation that governs the dynamics of the star. And this is exactly the same equation that governs a pendulum or a pen balanced in your hand. It's exactly the same equation. It's the equation of motion. And then you have to verify if the potential of this equation of motion, if the potential is as a positive or a negative concavity. So for those of you who have a mathematical background, what you have to do is to compute the second derivative of this potential and the sign of the second derivative. So if the potential is positive, the object or the pendulum, whatever, will start oscillating around the minimum. If the potential has a negative concavity and you move the point from the equilibrium point a little bit to the left or to the right, it just falls from the potential outside. So this is what you have to do. You have to compute the potential and check if the potential near the equilibrium point has a positive or negative concavity. This will tell you if the solution is stable or unstable against these radial perturbations. To do so, there is one extra thing that we have to do, which is to guarantee that the matter is conserved around as the star oscillates. So if the star is oscillating outside to the outside or to the inside, remember that we have a thin shell separating the two spacetimes. And so as this object moves outwards or inwards, there's going to be matter moving across this thin shell, this surface. So there is this extra thing that appears, this extra term that appears in the conservation equation that's got to do with the momentum flux across this thin shell. But then again, this is just an extra detail that appears here because we are dealing with fluid objects. For vacuum, for example, it's different. This term doesn't appear. But then again, as long as you understand the basics of what equilibrium, stable or unstable equilibrium means, these are just the extra details for those of you who are more into the mathematical details of the models. So to summarize, it all turns down to two things. If the potential of the solution has a positive concavity, the solution will be stable. If the concavity is negative, the solution will be unstable. So what we have to do is to compute this potential, the second derivative of this potential, so the concavity of the potential, and we'll be able to say if the solution is stable or not. So here are the results for the first model. In this plot here, we have the concavity of the potential, and as you can see, again, let me just remind you that the y-axis is the initial radius of the star, and the x-axis is the radius of the shell. And as you can see, there are indeed regions for which this solution is unstable. So if we start, for example, from a star with a radius 3, and you put your thin shell with a radius, let's say 2.1, you will end up in this point right here. This point is red, which means that the potential has a negative concavity, so this star is unstable. So what do we need? What are we looking for? Well, since we want to use these objects to replace black holes, we need the star to be stable, not always. We just need it to be stable when the size of the star is small enough to replace the black hole. So when the compactness of this star is arbitrarily close to the compactness of a black hole. And so if you look into this plot, this means that we are only interested in the radius of the shell going all the way up to 2, because the radius of an horizon of a black hole is equal to 2 times the mass. And so we are looking for stable solutions when the radius of the shell is 2 times the mass. And if you look here, into 2 times the mass, you will see that there is this very thin green line here, which means that the solutions, these star solutions, are stable when the thin shell is arbitrarily close to the size of a black hole. So the result is, if you take a shell like this and you put a mass, you put the shell with a radius just slightly bigger than arbitrarily close to, but slightly bigger than the radius of a black hole, this star will be able to reproduce 100% the observations we have for orbits around a black hole. So this is a very nice model. It is stable and it is made of regular matter. Let me just make a brief comment about one extra energy condition, which is called the dominant energy condition. This energy condition is not as used as the strong, the weak, and the null, but it also has some implications. And one very important implication of this energy condition comes from the year 1991, if I'm not mistaken, where Eric Poisson published a paper where he showed that there was a relationship between stability and satisfying the dominant energy condition. What he proved in his paper, was that every time the dominant energy condition was violated, the solution was unstable. Although this was not a one-on-one relationship, there were counterexamples on the other way around. He proved that every time the dominant energy condition was violated, the solution was unstable. And in here, this is not what we observe. So in here, we have this region where the dominant energy condition is violated, but still the solution is stable. So this is a counterexample to the result that Eric Poisson had almost 30 years ago. So let's now, by the way, this red line here, vertical red line here, is the Bookdahl limit. So as you can see, you can still go all the way to the arbitrarily close to the black hole compactness, and there is no problem. So the Bookdahl limit doesn't apply to these examples. For the second model, we have a similar result. In here, the horizontal line is the Bookdahl limit. You can see again that there is a region here where the solutions are unstable, but then again, the argument remains the same. You are not interested in the entire combination of parameters. You are only interested in the parameters there are in the parameter space. You are only interested in the radius of the shell going as close as possible to the radius of the event horizon of a black hole, because that's when the model is able to replace the black hole model. And if you look into this plot, this happens, again, as I said before, it happens when the radius of the shell is close to twice the mass. And so we need to take this point into consideration. And as you can see, if you move in the parameter space where my mouse is, you can approach arbitrarily the radius r equals 2 times the mass, arbitrarily close to this point, always satisfying the green, the positive concavity of the potential. So if you approach this point in this line here, you will always have a stable solution that satisfies the energy conditions. So again, this model can be used to replace a black hole by the same argument as the first one. And again, the dominant energy condition still provides a counterexample to the result of Eric Poisson in 1991. As you can see, there is a region here where the dominant energy condition is violated, but nevertheless, the solution is stable. So this is, again, something that contradicts the result by Eric Poisson in 1991. But nevertheless, the result of Eric Poisson was made in space-times without fluids, so just vacuum space-times with thin shells. So it was not guaranteed that his result would hold for objects with fluids like the ones I am presenting here. But nevertheless, it's important to see that this result is not general. And if you take fluids into account, the results change. So let me conclude my work. How much time do I still have?
Not so much, if you want to leave some time for questions. So
okay, so I'll be really quick here because
yes,
I'm waiting for your questions. And so the results are the following. The conclusions are pretty much the ones I have been saying over and over along the presentation. But there is much more work to do regarding these objects. So these objects are interesting, and they kind of are able to replace black holes, which was the initial objective. But now more questions arise, like, okay, so you have made an object that replaces black hole, but how do we prove that these objects are indeed the ones that are in space? Because, I mean, if the observations you have cannot distinguish between black holes and these objects, then these objects remain just a theory, right? There's no way to, if there's no way to distinguish, there's no way to prove that these objects are the real ones. And so my answer is that there are ways to distinguish these objects from black holes, just not from the observations I mentioned. So I stated orbits around black holes, and I stated the shadow of the object. These two observations will remain the same because photons and objects, like stars, for example, they are moving in the exterior region of these objects. And the exterior region is exactly the same if you take a black hole or if you take one of these fluid stars. But there are other observations you can make. For example, gravitational waves. If you have an object that does not have an event horizon and you collide objects like this to emit gravitational waves, the gravitational wave signal will be different from the gravitational wave signal of black holes. There are extra things that appear in the signal that do not appear if you are taking black holes. For example, since these objects do not have event horizons, you expect the gravitational waves to be reflected inside the object and be consequently re-emitted many times. And this causes the appearance of gravitational wave echoes. Gravitational wave echoes have not been observed yet, to my knowledge, but they are being searched for. If you find gravitational wave echoes, you are certainly not dealing with black holes as a final remnant of black hole collisions, and it might give you insights if these objects are real or not. Another thing you can use to compare is tidal effects, because if an object, like a neutron star, for example, if an object doesn't have an horizon, it will suffer tidal effects that are visible in the phase of the gravitational wave. So again, something you can do to compare. And also, if the final object resulting from a collision of two objects is something like this, in the ring down phase of the gravitational wave, where the object is just oscillating freely in space, the frequencies of the object oscillating will be different from object to object. So these frequencies have been computed not only for black holes, but also for other objects, but we have not computed the frequencies for these objects. So if you compute the frequencies for these objects, and you then compute these frequencies or observe these frequencies in the gravitational wave spectrum, you will be able to distinguish if these objects are consistent with what you observe in the gravitational waves or not. And just one final comment, these objects are not rotating, and in the universe, we expect all the objects to be rotating, angular momentum. And it would be very interesting if we could find fluids fluid spheres like this, that instead of being static are rotating. So that would be also a very important work to do based on this first paper. Thank you very much, and I'll be able to hopefully answer your questions.
Thank you, Joao. Very interesting talk. So we have some time for questions, about 6 minutes. If you have questions, please write question or Q in the chat, or you can also raise your hand in the participants list. Is there any question? Grace, go ahead.
Yeah, thank you for the talk. This is super, super interesting. It's more of a clarificatory question really about what the goals of this kind of research are. Is the idea that this might actually be what black holes look like? So black holes might not actually have this singularity, and this is like an alternative model of what the black holes really are? Or is the idea instead that it would be useful to have some kind of alternative placeholder model for a black hole for some other reason, say to do some other calculations, but that you don't necessarily actually believe that this model corresponds to the true internal structure of a black hole?
Okay. Yeah, so the final objective will always be to find a model of a compact object that can replace black holes. So you can observe, you can find a model that's being observed by an external observer. That's what we are. It looks exactly like a black hole, but doesn't have the problems of black holes, like singularities and event horizons. Now, if you ask, if I believe that these are the objects, I would say no for many reasons. First one is that these objects are static, and we expect objects in an astrophysical environment to be dynamical, to be stationary, rotating, etc. So this my argument with this object is that to provide a basis on which one can create more and more complicated models to replace black holes. So this is, I don't believe these are the solutions. I believe this is a first step towards finding the solution. So this is to provide the basics, to give you an alternative way of finding models that could replace black holes, and eventually taking these models as a basis, make them more and more complicated, more and more physically relevant, more and more astrophysically consistent, to eventually find a model that could replace black holes. That's the idea.
Right, that makes sense. Thank you.
Thank you for your question.
Eric.
So I think that these are really interesting models. To my mind, just for exploring the space of conceptual possibilities, if you like, what general relativity, in principle allow in the universe. But there are a few reasons why I'm skeptical that even with the very sophisticated elaboration, these kinds of models will be able to replace black holes. And primarily for two reasons. One is that we simply don't know of any actual dynamical mechanisms that could produce such objects, whereas we know lots and lots of dynamical mechanisms that we actually have very good evidence actually occur that produce black holes. The second is about the rotating objects. So I mean, first of all, that's going to be hard because we don't have any exact models. We don't have any exact solutions that represent bounded rotating fluids or dust. So it would be extraordinarily important in its own right if you could find exact models for that. But more importantly, bounded rotating matter won't have an ergosphere. So you'll never be able to replicate the behavior of quasars.
Okay, so first part of your question, yes, there's no mechanism that we could say clearly that the final object will be something like this. Of course, there are a few ideas towards this explanation, like for example, what happens in supernovae when the interior of this star explodes and releases energy. And this was exactly the first motivation towards studying spacetimes with thin shells, was that when the supernova, the interior of the supernova explodes, the matter is compressed in such a way that it kind of approximates to a thin shell. So for the problem is that, of course, supernovae are objects that are big, and they would never have the size that we need to replicate the black hole spacetime. So yeah. Of course, the mechanism to form this object is a problem, but then again, when we take just general relativity to explain how a black hole forms, again we are kind of, in my opinion, of course, there's many different interpretations, but I would say that we are kind of stretching general relativity to the point where we are not sure if general relativity works or not. So when we use general relativity to explain how a singularity forms, if we are not sure if the singularities even exist, because we might not be able to use general relativity all the way up to the singularity, there might be some quantum effects arising in between. Maybe there are some counter examples, maybe there are some other effects arising in between the initial state and the final state that in general relativity would be a black hole, that could somehow create an object which is not a black hole. I'm not saying that these are the objects, because again, I think these models are just toy models, just to provide the basis to more research. But maybe even if general relativity is valid, and it applies to stars, for example, and general relativity predicts that these stars collapsing eventually form black holes, maybe general relativity is not valid all the way to the singularity, so there might be other effects that prevent the black hole to form. As for your second question, I totally agree that we would need, in order to have a model that is completely consistent, we would need an ergo region. And yes, today we don't have any models that replicate that, and we don't have, as you said, good models for rotating objects. I think we still need to do more research in this direction, because there's a lot to learn. And,
yeah, absolutely, yes? I agree. Absolutely, I agree. You should definitely research that.
Certainly interesting.
Yes,
fascinating.
Yes. So Movin has a question. Movin, if you could ask your question in 20 seconds, could be great, because we don't have that much time. And the same for the reply.
Thank you. Thank you for your presentation. Well, my question is related, I think, somehow to the Grace question that asked. So imagine that I, I have an empty space, and I just put a spherical object into it. Okay, so this spherical object, if the radius of this object is just smaller than some amount of thing that we call it, for example, a Schwarzschild region, then it's going to be black hole. Or, is your work just show anything more than this? Because I think the black holes that you just show us are just included in the Schwarzschild black holes, I guess. Are there anything further that you can show us for this? You told us that they're new black holes or somehow, but I didn't really get the main point of it. Thank you.
Oh, if you could be very brief, and in the meantime, Grace, can you start sharing your slides, please?
Yes, sorry, let me interrupt my sharing. So really quick, as you said, and you're totally right, if you have an object that is smaller than the Schwarzschild radius, this object will collapse to a black hole according to general relativity. Now the thing is, if you have an object that is that the size of this object is arbitrarily close to the Schwarzschild radius, but just slightly bigger, it will not collapse. These are the objects I'm dealing with. I'm dealing with objects that are so compact that they are indistinguishable from black holes, but they are just big enough to not collapse to black holes. That's the point of these models.